Hello everyone, this is Vishal here. Today we are going to discuss on the topic homomorphic encryption. Let us look into a quick intro about homomorphic encryption. See, in networking or communication system, data often travels between client, service, and cloud systems. So during transmission or remote computation, the biggest risk is data exposure. Attackers might intercept or manipulate it. So homomorphic encryption helps here by ensuring data privacy and security even during processing or transmission. So why we are using mainly in networking? Secure data transmission. Normally encrypted data must be decrypted before use on the server. So with the help of homomorphic encryption, the server can process the encrypted data. For example, perform calculations or filtering or routing decisions without decrypting it. This prevents data leakage even if the server or network is compromised. So the next use could be cloud and edge computing. In the cloud network, sensitive data like medical or financial information can be uploaded in encrypted form. Thereby, we are reducing the data privacy breach. There is no privacy breach, we can say. The cloud performs analytics or computations directly on the ciphertext. Only the client, that is with the private key, can decrypt the final result. For example, a hospital encrypts patient records and sends them to a cloud AI model for prediction. The AI computes results on encrypted data, thereby no privacy is breached. Let us understand the homomorphic encryption concept through a simple example. So this was proposed by Craig Gentry in 2009. So the main objective of this model was to keep data confidentiality throughout the computation process. For example, imagine you lock your numbers in a special box and give the box to someone, that is, you are sending the encrypted message. They can add or multiply the boxes as instructed, but they can't open them. So when they return the final locked box, you unlock it to get the correct results. So whatever the modification, the addition or multiplication happening in between the encryption process after encrypting the message, so that added or modified result, when you decrypt, you will get the correct plain text. Let us now understand the working principle of homomorphic encryption. Say you have two encrypted message X and Y. So the cloud is now performing operation on the encrypted message. So that is encrypted of 8. Now this encrypted of 8 will be sent to another user B. They will decrypt the message using their private key to get the original plain text. So we have three different types of homomorphic encryption. One is partially homomorphic encryption, another one is somewhat homomorphic encryption, and the final one is fully homomorphic encryption. So what is partially homomorphic encryption? So it will support only one operation, that is either addition or multiplication. Example would be RSA multiplicative or failure additive, that is in between the cloud operation. So whatever the operation they are doing on the encrypted message, either it can support addition or multiplication. So now let us see into somewhat homomorphic encryption. So this supports a limited number of both addition and multiplication. So it is not supporting either, it is supporting both, but to a some extent, that is limited to some number. Fully homomorphic encryption. This supports any number and combination of operations on ciphertext. Extremely powerful but computationally heavy. That is, you can perform any number of addition or multiplication or even combination of both the ciphertext. For example, Gentry's FHE scheme first proposed in 2009. What are the key features of homomorphic encryption? Data remains encrypted during the entire process. So whatever the encrypted data we are sending during the transmission process, whatever the cloud modifies or whatever unauthorized access happens, the data remains encrypted. So whatever it may happen, they cannot expose to the original message what you're trying to send. No need for trusted third parties. As I explained in the example, let's take that hospital example. You are sending your patient record to any model AI to analyze their or to predict their health condition. So whatever you are sending, only the encrypted message will be sent to the AI, and the AI will predict based on the encrypted messages and does not expose to the patient's original record. So thereby we are reducing the trust for third parties. Provide strong data confidentiality and integrity. Since it is going to be a end-to-end confidentiality process, so whatever you are encrypting and sending to any user or your friend will be encrypted throughout the transmission process and cannot be exposed the original data, suitable for untrusted cloud environments. So it will be like whatever the cloud, whatever the environment you use, it can be wherever you can use. So whatever the environment may be, whatever the situation may be, and whoever the unauthorized access may be, you cannot decrypt the message unless or until you know the protocol. What can be the applications of homomorphic encryption? Now we are using homomorphic encryption in a number of fields. As I told earlier, in healthcare industry, so whatever, if you are going to analyze, say if you have some patient record and you're going to analyze their health data, so you're going to give it to a modeled AI and trained AI, where you will send only the encrypted data or not the original data. Thereby, you are preserving your patient's data and data confidentiality. Let us understand homomorphic encryption using a mathematical example. So we are using failure encryption be additive. We are assuming that failure encryption here used would be additive. So the equation could be E of A into E of B is equal to E of A plus B. To make it even more simpler, let us consider a real life example. Say you have a data set and you have data 5 and 3. Okay. So you are giving it to the server, you wanted to pre-process it or you wanted to process the data. So you are sending the encrypted message of A and B, that is X and Y in this case. You are sending it to the server. So whatever the server, so the server is now what is doing, now it is doing some modification E into X into Y. So that is on the encrypted message. So X and Y are the encrypted message. Now it is the cloud is performing X into Y, giving an encrypted message of E of 8. Now this E of 8 is again giving back to you, and you with your private key you will decrypt this as 8. Okay, so whatever the original text you are giving will be received, whatever despite of the modification happens in between the cloud or the server. Now let us look into the advantages of homomorphic encryption. So we have strong data privacy. So whatever the process, whatever the modification happens in between the transmission or in between the cloud would not be exposing the original data. So the only the whatever the modification happens, or that happens only on the encrypted data. Secure computation on third-party systems. So whatever you are sending the data to any third-party systems, it will be like secured. So no one can, explode your original data. Eliminates exposure risk of sensitive data. So exposure. So what does this means? So whatever the data you have personally, you are sending only the encrypted message, right? So thereby it is reducing the exposure risk of sensitive data. That is only the encrypted messages used throughout the computation process. So not the original message. Enables collaboration between untrusted entities. So when you have two users, okay, so you are not aware of any, like, unauthorized access may happen, any attackers may try to explode your messages. So this homomorphic encryption could reduce that probability, and thereby it is giving collaboration between untrusted entities. Limitations of homomorphic encryption. So it is highly expensive and high computational cost. Since it is involving a large number of encrypted message. So whatever, say for example, you have a message, hello, you are as a user A, and you wanted to send this hello to user B, say your friend. So this hello can be encrypted using any encryption algorithm such that it would be like a very bigger, the encrypted message would be very bigger. So there is a high chance that you cannot afford for it, right? So it is highly computational cost and slow performance, especially in FHE, that is federated homomorphic encryption. So slow performance. So due to the encrypted message transformation, so it is slower in performance. Large ciphertext sizes, as I have already told. So whatever you have message, if you are going to encrypt it, so it will be like a large ciphertext, large encrypted message. So complex implementation. So implementing homomorphic encryption is highly complex. So future scopes of homomorphic encryption. So we can improve the FHE, as I told, a federated homomorphic encryption using, we can optimize it, so thereby increasing the efficiency of the algorithm. Integration with blockchain and AI, real-time privacy preserving analytics, standardization for industrial and government use. So as I told earlier, homomorphic encryption is a revolutionary concept in data security. So whatever the data you have cannot be exposed at any cost. So enables processing encrypted data without revealing it. So we have seen through it. So whatever the data you have, only the encrypted message will be given, and encrypted message will be modified or processed or whatever it may be. And throughout the computational process, only the encrypted message will be used and not the plain text, and the plain text will not be exposed to anyone. So though computationally heavy today, it's key to secure AI, cloud, and IoT in the future. So whatever, so though it is, as I told, computationally it is heavily cost today, but it is highly secure to, to preserve or secure AI, cloud-based technologies and IoT devices. See, for example, you have a large number of data that cannot be exposed to anyone, right? So, in order to preserve your data for strong data privacy, we can go for homomorphic encryption. So, this is what all about homomorphic encryption. So, we have seen through its types. So, introduction, what is homomorphic encryption? We have seen through a mathematical example, its advantages, its limitations. So, hope you guys understood. Thank you so much.